are aquatic sensors. We do cutting edge water quality technologies that we realized there were gaps missing in North America. So we're very excited about finding new technology, bringing it in, making sure it's rugged, making sure it's affordable, and especially in this day and age when funding isn't on the forefront of anybody's budget. And that's why we're here today to present Bill Arnold and Ocean Space, because they are one of our partners that we work with. So that's my intro. And now I will give yourself, Bill, an intro as well. So he is a very unique natural-born Floridian. Not sure how many are left. He has spent his personal and professional life in and around water, both as a waterman and as a research scientist. He originated and led the molluscan fisheries research program for the Florida Fish and Wildlife Research Institute. It was there he developed an interest in larval ecology and population connectivity of sessile marine invertebrates, with an emphasis on hard clams in the Indian River Lagoon. Oh, excuse me. As some of you know, trying to track and model those patterns of connectivity is constrained by limitations of net-based sampling. It does not provide the fine-scale resolution nor the efficiency of data delivery necessary to conduct adaptive sampling. So to overcome these limitations, Bill and his colleagues formed Ocean Space. This was a means to design, fabricate, and commercialize a flow-through optical imaging system that could deliver zooplankton data characterized by fine-scale temporal and spatial resolution in near real time. And this is how the aquatic imager was born. So Bill, I hope that's a good introduction, and I'm going to now hand the microphone over to you.
Okay, thanks, Andrea. That was an excellent intro. I appreciate it. I do want to say a couple things up front. One is I'm going to be bouncing back and forth because the actual aquatic imager software is on a different computer. It has to be. This computer I'm working on now is not large enough. So please be patient. I think it's going to go relatively smoothly, but you know, I'm not a computer geek. I'm a biologist, and we definitely have our limitations. The other thing I want to say is thank you very much for attending. Your time is important and precious, and I appreciate you taking some of it to spend an hour or so learning about the aquatic imager. And I think you'll find that it's a unique and very adaptable instrument that you may find has applications for the work you're doing. So I'm going to start by giving a PowerPoint presentation and hope I can actually do this. Okay, I hope like heck you're seeing a full screen. Like I said, I'm a biologist. You have to go slow with us. So I'm going to talk about the Ocean Space Aquatic Imager System. It's a tool for monitoring zooplankton, larval fish, also microplastics, and really any other particulate that falls within the size range for which this thing is designed. Okay, so as Andrea mentioned, I don't do this by myself, obviously. I've got a very capable team. I'll start with Milton Dean up there in the upper right. He's our optics engineer, also well-versed in corporate administration. He's been a COO and et cetera, with a variety of companies. He's now developing, in addition to this, a medical device. So Milton's absolutely brilliant, ex-Coast Guard, just a wonderful guy to be around. And then there's Eric Steimel, right middle. He's our MacGyver. He can do just about anything from ROVs to, he's got a PhD in chemistry. Eric really is an amazing guy. And then there's the wild man of the group, and that's Kurt. He's the coder, software programmer. You know, he goes to bed at 9 a.m. literally, and he's up all night. And I have to close the doors in this room because he's on these computers and the lights are on and everything. You know, it's just that's what software developers do. There's just no getting around it. And then Carson Henwood, she's a PhD student now. I picked her up as an intern when she was at Eckerd College working under Dr. Nancy Smith, a zooplankton expert. So she got her training from Nancy. Now she's working under Kendra Daly over at USF on her PhD. And she's still a very important part of our team, although most of her time is now spent working through her core courses and setting up for her dissertation research. And then there's me, and I did want to say, Andrea mentioned this, but I've done a lot of larval work and published on it quite a bit. In particular, I remember the work I did in the Indian River Lagoon trying to track larvae, and we were doing it using a net. We were pumping water through the net at 25 stations in that lagoon, and it was very frustrating because it took us all day to collect the sample, and we were trying to look at connectivity, as Andrea mentioned. And by the time we got to the 25th station, everything had changed at the first station, et cetera, et cetera. And it was then when I started getting in my mind, we've got to come up with better instrumentation for this. And ultimately, it took a while, but I got with this team, and they really are the engineers and developed the product. I'm more of the applications guy. I know how it can be used and where it can be used. So that's my emphasis. Okay, so microparticulates in the aquatic environment. I say microparticulates because we're talking about zooplankton, but also maybe larger phytoplankton, micro plastics, et cetera, et cetera. Anything that falls within our size range, which is roughly 1 to 50 millimeters. And I'll talk about that a little bit. But the 1880s developed net sampling is what most people still use a lot. And this thing has a lot of pain points. And believe me, I know. My first year out of grad school, working at Harbor Branch Oceanographic Institute with Marsh Youngbluth. He was a midwater zooplankton guy, and we were doing a study on demersal zooplankton emergence in the Indian River Lagoon. I spent every day for a year looking through a dissecting scope, picking through those things, hitting the counting button. I mean, it was torture. Yeah, at least you knew what you were going to do every day, but there was probably better use of my time, and I would argue that for all of these students and technicians that are doing this kind of work, there are better ways to do it that are quicker and more efficient. And the aquatic imager certainly qualifies for that and would free up their time to do other things. Also, with a net sample, you just don't get temporal or spatial resolution within a sampling event. You tow that net and you get a single number across that span of coverage. There are 850 copepods, but you don't know where they were. Also, the resultant sample, as you see in that middle photo, can be full of junk. That's trichodesmium in there. And you've got to pick through all of that to get to the actual zooplankton, the organisms of interest. That takes a lot of time and creates a lot of frustration. That sample processing is time consuming. It's not very responsive because you can't adapt your sampling on the water. You might be looking at these samples a week later or even 3 months later, and by then it's just too late to respond. It's also very labor intensive, and because of that reason, not that reason alone, but because of that reason, it can be very expensive. And I've looked at some contracts for zooplankton monitoring in industrial settings for like 316, the entrainment monitoring the EPA requires, and those contracts are $100,000 or more. That's a lot of money, uh, especially relative to the alternative that we provide. And also, you need constant taxonomic expertise. I mean, these sorting houses are mostly taxonomous, and that kind of taxonomic expertise is degrading. When I started working at the Fish and Wildlife Research Institute, I worked with a whole host of taxonomists, some of the best around. They're all gone, and nobody's coming to replace them. So as that expertise degrades, it needs to be replaced with a permanent record. And the aquatic imager, the data we collect becomes a permanent record. So that's a really important aspect of this. And of course, it's not just net sampling. There are a lot of optical imaging systems out there as well. All of these systems, and I would say all of them have strengths and weaknesses, including the aquatic imager. We certainly don't have all the applications solved. We have our niche and they have theirs, and I think that's important to keep in mind. But I would say that ours is less costly relative to most of these other options. So this is our aquatic imager. Some of you have seen it before. It's literally about as big as a bread box, 21 inches across. You can see the measurements there, and the weight, about 24 pounds. You can carry it around with one hand, no problem. So it's rugged and it's flexible and it's small and easy to move. We put it in a Pelican case, take it on the checked baggage, or put it in the trunk of the car. It's really easy to get around. That's important because this is an instrument that's designed to be practical, to be used out in the field and used a lot. So it's a flow-through optical imaging system. It acquires and classifies zooplankton and other small aquatic organisms or particles. Like I said, it's lightweight, compact, and rugged. You can get flow rates through this thing of up to 6 gallons per minute. We generally operate between 3 and 6 gallons. When we're using the color aspect of this thing, you want to flow slower. So that's more down on 3 gallon per minute range. And when you're doing the grayscale, AKA black and white, you're more up to 6 gallons, although you don't have to flow at that speed, but you can get up as much as that. 7 micron pixel resolution, so you're able to see fine features. That can be really important when you want to look at appendages and setae, et cetera, et cetera. Uh, like I said, you can range your scan rate from 10 to 35,000 lines per second, and you balance that with your flow rate. So that's one of the many user controlled settings on the instrument that really allow each user to uh, collect images and look at images in the way that best works for them, because it can be a very personal uh, process. What one person thinks is the way they want it could be, very undesirable to another user. And we have our proprietary machine-based, machine learning-based software. It's artificial intelligence based, and that not just operates the system, it also collects, packages the pixels into the images, classifies the images. That's where the training library is built, and it enumerates within each taxonomic or particle classification. So down here in the right-hand corner, you can see a view through the imaging flow channel. And you can see that that rectangular space down in there with the light is actually the imaging chamber. It's 10 millimeters wide, 53 millimeters high. And so that's what controls the size of the organism. Now, if you wanted to look at bigger organisms, we could talk, but this is the present system designed really for, as I mentioned, zooplankton and microplastics, roughly 1 to 50 millimeters. Although we've looked at images as small as a half a millimeter, and one of our customers has looked at bivalve larvae down in the 250, 300 micron range. So there's a lot of flexibility there as well. This is what the images look like, not the color ones. Those are photographs taken through a microscope, and then I've put in images from the aquatic imager to compare. And you can see that they're very faithful to the actual organism. And I wanted to show you the one in the bottom center because that's a fish egg, and I show you a fish egg example, but also I just threw in the gelatinous organisms there because one thing about net sampling is gelatinous organisms get completely destroyed. When we use this system, those gelatinous organisms go through without any damage at all. And in fact, all organisms pass through the imager and come out the other end in perfect health. You can collect them up, you can flow them back into the ocean, and that depends because in certain settings, like on the back of a small boat or something like that, you need a pump to pull the sample through. And while we've seen organisms come through the pump without damage, there is a potential that the pump could impact them. But that's post passage through the imaging chamber. So when the organisms actually pass through the imaging chamber, they're as healthy and alive as they were in the natural environment. So that's just an idea of what some of the organisms look like. And these increments here, I should mention that those are 1 millimeter. So you get an idea of how small a lot of these organisms are. Oh, and the other thing is the copepods on the bottom right. There must be, copepods are very common in these samples, and they're very small, commonly 1 to 2 millimeters, and a lot of different species. So copepods are a big component of what we see, at least in our marine environment. Okay, so accuracy, how well does this thing perform? Well, this is data from Monterey Bay, California, not collected by us. It was collected aboard the Western Flyer by one of their researchers. And out in the Monterey Bay, there were really only 3 major classes, as you can see, Chaetognaths, copepods, and cladocerans. And what these plots show is how many reclassifications of the data, as we built the training library, were required to achieve 80% and then 90% accuracy in the classifications. And to determine this, what you do is you go through a sample and you identify and validate every organism, and then you do a confusion matrix, and that compares what the machine would have done with no validation against what you validated to determine how well they correspond. And you can see that in this situation with only 3 taxa, very limited, and that's important to keep in mind, we're getting on the first reclassification, like here, this is the original classification that the machine did without any input. And then this is the first reclassifications above 80% accuracy. And even, with the copepods almost 90, and also with the Chaetognaths, we're actually exceeding 90 because they're pretty unique looking organisms. So that's really rapid, successful classification. We are very pleased with this. But here's the caveat, and this is important. When you have a lot more taxonomic classes in there, you're still going to be able to achieve 80 plus, even 90+% accuracy. It's just going to take more reclassifications, more buildup of that training library, more validation of images to distinguish all these different taxa. So when we're working in Tampa Bay, this is just an example of 6 of the taxa. We probably get 35 or more taxa sampled in Tampa Bay. It takes longer, at least initially, to build that training library up to a point where you've got the robustness to get 80, 90% classification accuracy. And you can see with some of these larvaceans, we only had 18 organisms to work with, and 24 for the Chaetognaths. That's not many. What you really want is more like the 2,000 plus for copepods, and then you start getting pretty good classification. And as you can see, the percentage of the sample that we had to add to our training library was around 20%, which is a pretty small percentage. So with that 2,000, we're doing like 40 organisms starting to get good classification success, or 400. Ignore me. Like I said, I'm a biologist. But anyway, so this is what's involved in building that training library. But the key to this is once you've got your training library built, and of course, we've already done a lot of work on the west coast of the United States, in the Northeast, in the Gulf of Mexico, and off Southeast Florida. So obviously, that's not everything, but it does at least give a start point for that training library. And our training library is available to the users for their start point, although I would point out you'll probably want to build or add in those organisms that are most dear to your heart and that are maybe, at least to some degree, unique to your situation. So that's important to keep in mind. Okay, so here's another application of these plastic resin particulates. And the plastic industry is really interested in this because there's a lot of spillage associated with them of these plastic particulates, and they're looking for ways to track and identify where the clumps of spillage are so that they can clean them up. And they're being very conscientious about this, and we appreciate it and think we have an ideal tool to help them in that process. So what I did was run some plastic particulates provided by a researcher through our desktop imaging system that you see here. And this is here's the injector over here. And this is nurdles. I call them nurdles, but it's not really the appropriate term for them. They're plastic resin particulates. They float, which is good because ours is a roughly surface sampling. We've been down as deep as 5 meters, but this is not something that's going to go down to 300 meters or anything. Ours is shallow water and superficial sampling imaging system. However deep you can draw water to it, but it doesn't go down to the sample. The sample has to be brought up to it. So we injected this through here, and this is what we saw. These are plastic resin particulates, beautiful images of them. You can see that they're roughly 8 millimeters, 5 to 8 millimeters. And then one thing about injecting them all in mass is they tend to clump up. And this is an issue you wouldn't have out in the field when they're far more spread out. But even so, you can see them very clearly, and you could assign this as a classification as class plastic particulates 1, 2, 3, 4, 5, 6, 7, 8. And then you would know how many are in there. You could have that for, class 1, class 2, et cetera, et cetera. So anyway, we're excited about the opportunities for the particulates applications. But there are other applications as well. One is vessel deployments. We've deployed this aboard small boats very nicely. the last 2 weeks, we had it aboard the research vessel RV Weatherbird out of the Florida Institute of Oceanography, and also the guy who took it out on the Western Flyer off the West Coast. And it just snaps right into their inline water flow system. This took me about 5 minutes to set this thing up. And then we ran it literally for the entire 2 week voyage. We had flow going through here, and we would do intermittent sampling, and we would do the intermittent sampling remotely. None of us went on the cruise. We had a Starlink satellite linkage, and with that, we could turn the start sampling and do all the things that the imaging system does from the comfort of our home, me here in St. Petersburg, and then Kurt out on the west coast of the United States. And one thing we're working on, primarily with Sea Robotics, is to install this aboard uncrewed surface vessels, which I think is a fantastic opportunity. Not something like the sail drone so much because it doesn't have the power. But when you start getting into these larger ones with banks of lithium ion batteries on them that have thousands and thousands of kilowatt hours, we require about 150 kilowatt hours to operate this thing. Then you can really put it out there and do long-term runs. And I think there's great potential for this because the uncrewed surface vessel industry is expanding rapidly, and they need to broaden their scope. They're doing mostly bathymetry in the scientific realm, and in my opinion, they need to broaden their scope and start doing more environmental and ecological monitoring. And the beauty of the system is, and I may have mentioned this, you get this second scale timestamp to every image. And with that, you can align the images with the GPS information, and then you can map. And you can see here, thank you, Maureen. Maureen Goff developed this GIS overlay of copepods off the southeast coast of Florida. And you can see they're not evenly distributed. There are hot spots. The red ones are the hottest of the hot spots, the orange are hot, and then the yellow are not quite so abundant. And that's really important because now you can start overlaying this with temperature and salinity and other things that are collected on similar time scales, and understand not just where the organisms are, but what's driving those distribution patterns and how it's differentiated amongst taxa. Because this is copepods, but you could bring in the larvaceans and the chaetognaths and the ostracods, and they're not all going to have these same distribution patterns, and start understanding, the real fundamentals of ecology relative to what's driving these populations and where they are. And this study was looking at giant manta rays, and giant manta rays are grazers of zooplankton. So we were working in this place where it's an oligotrophic environment, but it's a nursery ground for these huge animals. And NOAA wanted to know, well, how are they surviving? And this showing this patchiness, and of course the manta rays know where these patches are. They attack the patches, but that's important to know because now you can guide vessels to avoid them, and things say this, here's where they're going to be and here's where they're not going to be. So there's a lot of management implications to this as well. But that's just one thing. We've also developed systems for sampling from small streams all the way up to open water. And a lot of this can be done autonomously using not just Starlink, but any other kind of satellite connection or any other connection, remote virtual connection that you can set up to operate the system. So I think that's really exciting as well. We've also worked in industrial settings. The one on the left is a power plant up in Long Island Sound. They wanted to look at what's being entrained into their cooling water. And then on the right is the Carlsbad desalination facility, and they wanted to know what's in their feed water. Now, the difference here is in a cooling water situation, and John knows this very well, some of these organisms, and maybe a lot of them, are coming out the other end alive. It had always been assumed that it was 100% mortality. On the other hand, in a desal plant, there is 100% mortality, at least of organisms that are half a millimeter or bigger, because they're going through, screens that are on the micron scale. But we set these things up in these rugged industrial settings. The system worked like a charm. We were, again, just like we did on the Weatherbird, that's a Starlink satellite antenna sitting on top of that cabinet. And we remotely controlled this from St. Petersburg. It was out in Carlsbad, California. Oops. So that autonomous operation, we used Starlink. It worked great. It really did. There were a few downtimes, but that's getting better with more satellites. Our command downloads were almost instantaneous. The uploads took a little while, but still you can upload your data to clear off the hard disk to make room for more data collection. And the whole thing was relatively inexpensive, in our opinion, 165 monthly fee plus startup buying the antenna, et cetera, et cetera. We used virtual sits. I've got that picture of the cabinet showing everything in there. We had virtual switches and a UPS power supply, and the thing just really just ran on its own and did a great job. You can't say that a lot about a lot of sampling systems, especially biological sampling systems. And then it's a great teaching tool, and it's being used for teaching uh, both at Baylor University and at Eckerd College. This is a pre-college camp at Eckerd College just a couple weeks ago, and the young student on the left is still staring through that dissecting scope and still suffering, as I did my first year of working in the business. Whereas the center one shows the two young women injecting their sample, and on the right, seconds later, they're looking at the outcome and dealing with the data. So that's the sort of thing that can be done, and it saves a lot of time in the classroom because the students don't spend all their time looking through the scope. And as the professor said, it gives her a lot more time to teach them other aspects of zooplankton ecology, statistics, et cetera, writing reports, all those other things that are so important to science. It's not that identifying your organisms isn't important. It's just you need to be able to take those data and do something with it. So that's what I've got. If you want to ask any questions right now, I'm going to stop sharing and shift over to the other computer so I can show you our software.